right, welcome to Earth Science, everybody. It's time for the last lab. You made it. And it's a bit tricky, but I'm going to take you through it. All right, radioactive decay, radiometric dating. What we're doing here is continuing our work on thinking about how did we figure out how old these rock layers are, what layers are older than others, and so on. What you've done so far with relative aging and some of those principles, with correlation and some of those principles, what we've done so far is we can pretty safely say now, okay, if we go out and look at the rock in Pulaski and say it's Ordovician in age, and then go up high in the Finger Lakes and do the correlation and see that those rocks lie on top of the rocks that we have here, higher up in the section, therefore they're younger, maybe Devonian age, definitely Devonian age. But how is it that we got down to getting these numbers here? We haven't done that at all. How do I know that the Ordovician? I mean, we made up these numbers, right? We made up the definition of what Ordovician is. Stratigraphers argue over this stuff, right? So they got that set. But how do we have numbers to go along with these things that we've defined? How do we have numbers to figure out how old the planet is? You can't just do it with relative aging because all that tells you is older or younger. An example I used of this back when we started all this dating stuff and aging stuff is I'm older than you. That's relative. And then if you were to say you're one of you turned 16 today, if it's your 16th birthday, there's a number. I'm 42, I think. 42 is a number. That's an absolute age. So that's what we're getting at today. How have we done it? How have we gone back? And there's nothing, what is within the rock that will let us know how old that rock is. And it's a little complicated, so hang in there. So let's do it. Radioactive isotopes like carbon-14. If you've done anything with chemistry, maybe you're used to writing things like CO2, where the numbers down there. You don't have to write this in your lab. Don't worry about it. These are isotopes. These are forms of these atoms that are a little bit funky in terms of what they have inside their nucleus. You'll do more of it when you get to chemistry and physics. So we're going to say that they're maybe just kind of oddballs. This is an oddball version of carbon-14, an oddball version of potassium-40. In fact, it's such an oddball that we call it unstable. It's not happy as it is. Now, it doesn't have feelings. It's a carbon atom. But that's the idea of instability. It's not happy how it is. It's going to disintegrate. It's going to break down to a more stable isotope, nitrogen-14. This one breaks down into these ones. This one breaks down into this one. By the way, this whole entire thing is right on the front page of your reference tables. Okay, let me grab it. Yours is probably, you're looking at a digital one, but there it is, front page right there, that exact thing. So when you get down to the questions, which some of these are tricky, I'm going to help you. You're going to need to come back and look at that. So keep in mind that exists. So radioactive isotopes like carbon-14, this we will write in there, randomly decay down to a more stable isotope, and in this case, it's nitrogen-14. A random process, though the amount of times that it happens over a given time period is predictable. Which sounds weird that if it's randomly happening, how can we get a predictable rate out of it? And the way that we're going to mimic that is by rolling a whole bunch of dice. This is going to be the same process. Dice rolling is a random process, but you'll see that when we do it and we do it and we do it, if you do it over enough trials, get enough numbers, the results end up being pretty predictable just by the rules of probability that maybe you're working on in math class. So what we're going to look for is what is the amount of time it takes for half of a sample to decay. I've got 100 six-sided dice back there. We're going to roll them, and we're going to say that if it rolls a 1, it decays. It's gone. It's now a stable isotope that doesn't get re-rolled. How long does it take to get through half of those dice? And this rate is known as the half-life. Which, see right there. All right, so we're going to need these half-lives when we start doing the real work with the real questions, which, again, it can get a little tricky. If you're a little foggy with your scientific notation, 5.7 times 10 to the third means to grab that decimal and move over 3 times. So in other words, this is really 5,700. This one means grab that decimal and move over 9 times. So that would be, I'm going to type rather than try to write it. That many. How much did it help? 1.3 billion for potassium 40. Okay. These ones are much longer, which is going to be an important idea because 5,700 is not going to be long enough as a measuring tool to measure things that are like really old on the planet. All right. So what we're going to do now, I usually do this in class where all the students stand up, we're all rolling dice, and then you sit down as you do it. Now we're doing this on YouTube. I'm going to be back there rolling, starting with 100 dice, rolling over and over and over again, pulling the ones out as we go, and going. So I wouldn't say. Let me pause and think about how I want to say this. All right, so let's just basically cross this off. So we'll say dice. In this example, are like the unstable isotope. Okay. Now, normally every student has 1 die. They're standing up and they're going to sit down when they roll a 1. So rolling a 1 is the moment that the isotope decays. Again, I'm going to be doing this on my own since we're in this COVID situation. So when I roll a 1 with one of those dice, I pull it out and I put it into a beaker, and then the other ones go back to be rolled again. So that means that the sitting down students are basically we'll cross that off. Sorry, I should have done this ahead of time. The rolled ones, if you know what I mean by that, all of the rolled ones then have decayed down to the stable isotope. All right. So once we do this, how can we figure out half-life? Well, the answer is, how long is it until half of the students sat down or half of the dice decayed? All right. Now I've done it already. I did it maybe 5-6 times. I taped one of them. I was going to try to tape it and have you guys write down the numbers as you go, and it wasn't working. It was chaotic. Plus, once I did it, I realized I probably want to do this a bunch of times and get averages, which is going to make a lot more sense. So I've done that already. If this worked, what percentage of students would be left after 2 half-lives? That's a great question. What do you think? After 0 half-lives, I've got all of them. After 1 half-life, I've got 50%. And what some people think is, okay, the second half-life, then you get rid of the other 50%. Is that true? Shouldn't be the case. If you get rid of half each time, you start with 100%, you get rid of half of it, you're down to 50%. You get rid of half again, and you are down to 25%. Okay. Now, I've also got the D20, 20-sided dice. I'm not sure if I'm going to do this year. It took me like the whole afternoon just to do a whole bunch of trial with 6-sided dice. Maybe tomorrow with some of the blue team folks, maybe we'll try it in class just to see what the heck. But I think we can get to the ideas if we just do the 6-sided dice. But I asked in that video, what would be different now that you've seen this with 6-sided dice? What would be different if I tried to do this with a 20-sided dice? Okay. So what I'm going to do, I think we'll jump. I'm going to pause. I'm going to stop this. Look at your survival guide. You're going to go to the next video on YouTube, which will show you a couple of the things we were doing back there. And then we'll come back and look at some of the numbers we got. All right. Sound good? All right. Good luck. We'll see you in a minute.